this area has a lot to do with sustainability issues that are prevailing in the area of engineering nowadays. For the next 3 lectures, I would be addressing the topic of sustainability and sustainability development, which really has a big role in the geotechnical engineering. In this lecture, I would like to acknowledge the contribution of my student, Ms. Pinom Ering, and today the presentation would be on sustainable development and energy technology, geotechnology, potential role for geotechnical engineering. As you are all aware, what is happening is that people are looking at the critical issues like economy, and we need to have the society and environment. The interaction of the 3 pyramids, the so-called economy, society and environment, they are related. For the development of the quality of life of the society, you need to have a good environment, and also the solutions have to be economical to the extent that they should also not damage the environment that we have. So, these 3 pillars of or the pyramid, this structure has something common, like society needs good environment and also good environmental solutions, but all the 3, society, environment and economy, they need sustainable solutions. What it means is that the sustainability is something that we need to define in this context, that we need to use the materials, natural materials that are available today without affecting the needs of the future generations in a way that does not affect the environment, that does not affect the economy, and also creates to general well-being. In this context, the role of geotechnical engineering is very significant. I must say that not just apart from environment, it is also more about energy reuse, energy use as well. I would like to just present some ideas on this today, and also understand or establish research priorities and offer suggestions in engineers who are practicing to get more involvement in the area of sustainability. We also talk about salient issues related to energy geotechnology and the sustainable use of geomaterials and the potential impact of the climate change in geosystems. We would like to see also explore certain non-standard geotechnical conditions that may arise and propose an in-depth reassessment of the geotechnical curriculum in view of the sustainable geoengineering. What we studied so far in the ground improvement areas is that, for example, if there is a civil engineering structure, earlier people are going for pile foundations. Of course, even now that is the order of the day, but then if they can be improved with say for example, stone columns, a simple example, that is a big difference, like say for example, the consumption of the carbon in the case of cement and steel is much higher, and whereas you are trying to use some sort of a stone or some other aggregated materials in the case of soft soil when you want to increase the bearing capacity of soil. What I mean to say is that if you are trying to improve the bearing capacity of a soft soil, one solution is that you try to use some sort of columnar structures where the soft soil you have, say for example 10 kPa of shear strength, and you would like to improve the bearing capacity and reduce the settlements. Instead of the going for pile foundations, the stone columns is one viable option, or geocentrics is another option, or geocell foundations, depending on many varieties of, you can have varieties of solutions, but at the same time you need to understand what is the impact, or what are the impact in terms of sustainability that you are trying to contribute. We will discuss some of these things in this class today, and as I just mentioned, sustainable development means you are trying to meet the needs of the present without compromising on the ability of the future generations to meet its needs. And the development of a sustainable world will need a very deep understanding of the global processes that are complex, There are many of them physical, biological and human systems. And nowadays, and the current scenario is that many of these factors are interrelated and they negatively impact the quality of the life. Whether in the developed world or developing world, the things are happening because you are trying to make efforts in the developed world and also in the developing world. And in the developed world already there is a lot of consumption of the carbon, and then they are trying to understand what is how can you go on from now on. And particularly in the developing countries, there are a lot of construction activities that are coming up. Is it possible to really look at what is sustainability in this context? So why these things have become necessary is that you have increased energy demands, like energy requirements are too high nowadays, and they depend on the fossil fuels. So there is an accelerated use of the natural georesources, degradation of natural ecosystems and global climate change. These problems threaten to significantly disrupt the balance of the global physical, biological and human systems. For example, there is a rise in temperature. People are aware that 20 years back it was not that bad, but now you see that there is a temperature rise, and you see that lot of hills are being destroyed to construct roads in many areas, and definitely the ecosystem that you have in the form of hills cannot be destroyed just for certain construction in the civil engineering. You need to really see that you need to balance the requirements of our requirements, and also see that they do not affect the way we live. So all engineers need to understand and make significant contributions by solving the sustainability crisis. It's very important. And I would like to say that the energy crisis, though I may say that how is that geotechnical engineering is related to energy. You see in a minute that they have a significant role, particularly in terms of geothermal energy and other issues. What are the immediate threats to sustainability? One is that the use of natural resources is at a rate that will limit the ability of future generations to obtain and utilize resources such as fuels, water and air. So you should not use the rate of use of the natural resources should not be so fast that it will affect the balance or the needs of the future generations. That's one thing, like material requirements, as I just mentioned, the aggregates nowadays you normally the code specify good quality aggregates, but then you don't have good quality aggregates. Then in this context, why don't we use recycled aggregates or some materials that are stiffer and still serve the purpose of virgin aggregates? Then fuels, the thing is, now we are living on a lot of petrol and other products, but is it possible to have some alternate source of fuel for heat generation? Of course, water has been another premier important, water and air, we need all of that, and we should see that these things are not affected. So the degradation of the natural systems to a point that may jeopardize the beneficial balancing actions is something that what we know is that if you the natural system should not be degraded, and then we have to have a balanced view of what we need and what you can use. That's one thing. And the global climate change crisis is nowadays that we are all hearing that there is a temperature rise, there is an increase of carbon in the atmosphere which leads to increase in temperatures. They have links to anthropogenic effects and or the man-made activities. They have a big role in the stability of the Earth's climate, resulting in significant and potentially catastrophic warming of the Earth's atmosphere and oceans and concomitant rise in the sea levels. This is a very significant point, and in this context, how this geotechnical can address is something that we need to see. I'll give an example. It's an estimate that in 2007, the world consumed approximately 504 exajoules of energy. 1 exajoule is 1018 joules, and this is equal to 12 gigatons of oil equivalent. So, this is something that in 2007 12 gigatons of oil were used, and out of which 81% of which was derived from fossil fuels. Is something that is very alarming, that this sort of reliance, like on the fossil fuels, like you are trying to get all the energy from the fossil fuels, is not very sustainable. This is a very serious issue, and though we may have large reserves of coal, oil, shales and possibly methane hydrates, fossil fuels are ultimately exhaustible. So, everything is finally going to have everything is finite, and the possibility is that you are going to exhaust them sooner or later. For example, the world's resource of the coal, about you have 1600 gigatons, would provide 2.5 kilowatt per person for the next 100 years, and of course, that definitely after 100 years what is something that you need to understand. Similarly, oil and natural gas are limited. So, we need to understand that if you are trying to use or work on fossil fuels as a source of our quality of life, definitely they lead to a lot of issues. The fact that you have been using the fossil fuels only in the recent times, it is not there. Petrol use was not there about 100 years back, so much use was not there. Nowadays, you see that the use has been so much that the current predictions of reserves, the age of fossil fuel will be very short. So, this is something that we need to understand. And for example, as I just mentioned, how is that global temperature going to get changed? You can see that in the year 1890, there was some temperature here, say global mean annual temperature in centigrade, it is about 13.5 here. You can see in the year 2010, it became about, there is a 1 degree rise in temperatures. This is a big average, big change, because though this is a mean average, it means a lot for the ecosystems. So, this is like, say for example, the melting of the snows, melting of the changes in ocean levels. There are many issues that are connected with this, and the climate change that we have been seeing today is as a result of this point. And you look at carbon emissions that we see, like which are supposed to increase the temperature in the atmosphere. You can see that in the recent times, in the last decades, the fossil fuel carbon emission in million tons of carbon is about very high, it is about 8,000, it is just increasing too much. So, your objective is to save this energy and also to contribute to some extent. The relationship between the fossil fuel use and the global warming has been understood through the use of increased CO2. Like we know that increased CO2 levels will increase the temperature, and this has been understood very well by climate modelers. And the current concentration of the CO2 in the atmosphere is about 380 ppm parts per million, and research suggests that a concentration of 550 parts per million could trigger severe climate change. This is from IPCC 2000 report, that if you have further increase in the carbon content or the concentration, the problem is that the climate changes are going to be much more drastic if there is some increase. So, the objective would be now that how do you stick on to this, and people estimate that the 550 ppm will be reached by the year 2050, and unless you take a decisive action by all the communities, it is not easy to control this concentration of the carbon. Efforts to control global temperature changes to a level considered acceptable will require curbing CO2 emissions, so that a concentration in the atmosphere remains below 380 to 450 ppm. It is a very, there is now a specification which something is okay, like one can look at it, and people need to work back that what a particular nation should do, or what a community should do, or what an international community, all of us should do together to see that this limit of 380 to 400 or whatever you say has been added to, and we should never reach this limit of 550 because that leads to lot of climate change. So, to achieve these goals requires a reduction in the projected CO2 emissions to the atmosphere by many gigatons over the next several decades, and people always say that this is a gigaton problem. So, most of the strategies proposed to date such as improved gas mileage for vehicles or improved power plant efficiency do not explicitly involve engineering, geotechnical engineering. You must have seen that we have fuel efficient cars, but it does not mean anything. Say for example, you may have instead of 10 kilometers per hour, you have an engine which has some 15 kilometers per hour, but then there is still a consumption of the gas, which is something very problematic. Then they're all, the thing is, all disciplines, whether it is all branches of science and engineering, need to look at how do you reduce this carbon print on the atmosphere, and actually geotechnical engineering is one big way. If you have proper understanding of the geotechnical engineering principles and ground improvement principles, it has a very, very important role in the carbon print reduction. So, I will just introduce some principles here, a brief analysis of processes in which geotechnical engineering can help and reduce this issue. This is another figure which shows that you have from 1955 to 2105 the time scale, and you have carbon emissions in gigatons per year, So, up to 2005, this is whatever has happened. But then you continue at this rate, what happens? Definitely you are going to be on a high scale. So, then objective is to, the rate has been at 14 gigaton of carbon per year. If it just goes, it is going to be significant, but then you would like to reduce them in some way. So, you have to reduce to some levels. So for example, if you are aiming at a very good reduction of 70% reduction, and there is some way, like you have different wedges drawn here to see that, you need to identify what should be done from here. You should be able to control, see, this is called stabilization wedges. You do not want to really go follow this level, but then we would like to reduce by some levels, like come back, you reduce the slope of this line to this level, or if you are trying to reduce these are reduction wedges, you try to really come out with some strategy of stabilizing or reducing. This is the point here. So, you need to come out with various methods of coming out with this plans, so that the ultimate carbon emissions will not endanger the atmosphere. The people have been working on this particular point nowadays. Like I was in one conference in US about 3 months back on geotechnical engineering and how geotechnical can help apart from ground improvement energy. See, it has become a topic called energy geotechnics, where you have multiple ways of handling the ground engineering problems. Nowadays, the ground engineering has been not just limited to ground improvement. The concept is that you have an all-encompassing attitude that helps the globe, like reduces the global warming and also provides energy and energy recovery, waste recycling. Suppose there is a waste material that can be used in a road project, definitely it leads to a consumption of a reduction of carbon emissions. So, people have been talking about this, and in this context, the coining of the term energy geotechnology as a part of the ground improvement is something that needs to be accepted. The main source of energy are the petroleum, and about, say for example, 34%, you have coal 26.4%, natural gas about 21%, combustible renewables and waste about 9.8%, nuclear power 5.9%, hydroelectric 2.2%, the other mainly wind and solar. Of course, the efforts have been less in this, and as per the 2007 data, and of course, it varies, it is a general thing, but then different countries have different numbers in this area, and definitely people have been different countries have been placing energy, the emphasis on, say for example, nuclear power. They are trying to place emphasis on hydroelectric projects and also on the wind and solar energy, and the fact is that people have been trying to make all out efforts to see that this concept of energy using geotechnical principles can be helpful. And as I said earlier, 81% of the energy consumed worldwide is obtained from fossil fuels, and primarily because of the low cost under present conditions. Why is that people are trying to go for this fossil fuels? Because now we are trying to remove the say for example, petroleum from some places. Because of the investments that are required and the cost that are involved, it has been low. But then if you do an analysis in terms of the climate change and its effects and all that, maybe this is not acceptable at all. Say for example, the concept of life cycle costs, like or the emissions reduction or emission increase because of using a particular technique over a long period of time, needs to be understood in terms of the life cycle costs. Even in the life cycle costs, for example, if somebody is working on how much is a life cycle cost after 20 years, and maybe that is a better alternative, possibly you must go for how much of carbon reduction footprint is there after say 10 years or 15 years. That may be a better basis than trying to simply go by life cycle cost analysis in terms of currency. So, what I want to say is that the fuels which are emitting lot of carbon dioxide, which gradually accumulates in the atmosphere, leads to anthropogenic driven climate change, needs to be avoided. This is what I would like to say. And the current global energy consumption rate is about 15 terawatts, and there will be a pronounced increase in the energy demand in the next 25 years because everybody is looking for economic development, and there is also population growth. If you look at these two factors, you can say that 17% increase if consumption population growth continue at the current rates, the business as usual option. One way of looking at the problem is that just do as it is and have the practices that you have. So, the 17% of the 17% increase in the consumption and then population growth, the 17% increase is in terms of for the energy requirement. It is huge, 17% increase is huge. And the second thing is 66% increase if consumption in the underdeveloped countries world increases to levels required to attain proper quality of life. We know that the quality of life in some countries is not good, and of course, the way the quality of life is defined is something that needs to be examined in detail in the context of what consequences it has. Like 66% increase is a big increase, and suppose you want an underdeveloped country, they want to have they do not have fuels, and then they would like to rely on fossil fuels and burn their existing options. Then the problem is that it leads to very significant effects on it is a big bearing on the energy demands as well as the climate change as well. So, what people have been trying to do is that people are looking at geothermal energy as a source of energy. It is nothing but people are say for example, deep geothermal energy systems are there. They extract heat from hot rock formations. You have hot rock formations underground in this earth, where the temperature is about 350 degrees, to produce steam that can be used directly to provide heating or to generate electricity. Many countries have been doing experiments in this direction, and conventional geothermal technology focuses on energy production from rare near surface hot spots that are sources of steam or hot water. So, for example, in Himalayas and other places, people are aware of the hot springs that exist, and people, if they have some information about the hot springs, can it be used to obtain geothermal energy is something that people are also looking for, because say you have a hot spot in Himalayas which has no electricity, possibly that is a good option to irrigate or to provide electricity to villages nearby without too much of effects on other lives, other issues. So, the vast majority of the world's accessible geothermal energy is found in hot dry rock, and the reservoir must be engineered for energy production. Actually, the thing is, it is not, it is the hot temperatures exist about, as I said, much deeper, and you need to have engineered systems to recover the heat from the deep strata within. So, what you have enhanced geothermal systems, and we call hydraulically fracture the formation to increase the hydraulic conductivity and surface area for heat exchange, like heat has to come out. So, you need to hydraulically break or fracture the formation so that the heat can be recovered. Of course, one should look at long term consequences of fracturing and also its climate, its effects on subsidence, and there could be many issues people have not understood, though people have been mentioning about the use of the geothermal energy now. So, the use of geothermal energy is an appealing strategy for the reduction of carbon emissions. Except for the construction of the power plant itself, carbon emissions from geothermal plants are virtually nil. So, what it means is that you are just tapping the energy that is available and trying to direct to places where you need it. Like, say for example, this is a typical figure. You have at the deep temperatures, you have injection wells, then you have a production wells where you can recover that energy. Okay. You have deep geothermal recovery for electricity generation. Then there are also ways of distributed geothermal storage and recovery systems at shallow depth for residential purposes. So, there are certain issues where for houses, say particularly in places like Himalayas or even in the UK and other places where the climate is very cold in winter, people use room heating, which is quite a source of energy, which is a big source of energy, consumption of energy, and people have been really looking at this sort of options where you try to obtain the geothermal energy from ground and use it for room heating. This is for houses and apartments. In fact, people have what is called energy piles. I had to, there are a couple of groups working in the world, like I am aware of the work that is being done by in UK, where particularly in the University of Cardiff, where they think that the energy piles could be one option to reduce the load because of the room heating requirements. And some municipalities even say that our strategy is to have energy piles as a source of energy and eliminate the need for having room heating, cooling systems and heating systems based on this type of conventional systems by certain periods, say for example 2020. I do not know how much is it realistic, but then people have been making efforts to see what is the amount of energy that one can recover. There is another place where I was in Monash University in USA, where under the guidance of Professor Malek Bawaza, people have been looking at the energy. The pile acts as a the source of it has certain, it's a steel pile in which you try to tap the energy from within ground and see that you are trying to estimate how much is the energy that you can get from the underground sources. So, these are all some examples, and very importantly, whatever you do, like you are looking at sustainable geothermal systems, which means that they should be useful in terms of it's a source of renewable energy, number one. it cannot be an energy that gets exhausted. So, you must have a time scale for these systems, say for example, how can you make this geothermal systems very effective in 10 years? Like one serious issue that I always feel is that in apart from geothermal energy, solar systems, in fact, world energy systems have certain impact where in India it's common practice that in many villages you don't have power in summer, and the summer you have sun which is burning, so at 45 degrees temperature, and if you have some sort of heat recovery systems, energy recovery systems, and also the proper piling, proper foundation systems where the energy can be stored whether at the top and bottom, and there could be a sort of a system where for some years, for based on certain calculations, if you can establish that you do not need energy from the conventional sources, and the energy from bottom, the geothermal systems or even from solar systems is sufficient, will be a big contribution. I would like to give an example in this connection. There was one field trial that was the field trials are being conducted in Ahmedabad, where conventionally we know about canal lining, and we estimate that the canal lining will lead, proper canal lining systems will lead to reduction in seepage, and so that the water that is being carried by the canals reaches the destination. And always people have a prediction, some 20% loss of losses they expect in water transported, which is, say for example, if you are trying to transport some between two places 15 TMC, 1000 million cubic feet of water between two destinations, 15 is a unit, and you have 12 as a number that you need to consider, and you expect about 3 tons being lost because of evaporation. What was tried in Gujarat was that they were trying to cover all these canal tops with solar panels, with the result that the solar panels that are there, you can directly tap all the energy from the sun, and also they act as cover to reduce the evaporation losses. So, that is a wonderful idea that people have been trying to use, and so in one shot you are able to reduce the so called evaporation losses, and also reduce the power required for additional 3 TMC feet of water, which is something very good. Like you are able to and then apart from it, the biggest gain was they trying to get the electricity from the solar panels that are being used as covers, and all the villages nearby can be electrified, or energy can be supplied to all the villages nearby, with the result that the requirement that the particular area has will be much less. It is a wonderful thing, though it is not directly doesn't involve in geotechnical engineering principles. The fact is that the common sense applications of energy systems have been made use of in this case, to see that the energy that needs can be really energy required can be a little bit lessened. So, this is what I meant by sustainable geothermal systems, and so in general, definitely geothermal systems you need to really they should be for sustaining for about long term. Say for example, if you are looking at the geothermal energy, definitely you must be able to estimate the time scale for the reservoir. Then early depletion is another that has a problem. Like for example, you have a particular source and there is a problem that the energy gets exhausted quite fast. Then one should be careful, because the fast recovery in the beginning of the operation enhances early return on the investment, but disregards the long term performance of the reservoir. So, you should strike a balance between the energy, the depletion of the or the for example, you would like to store all the energy in terms of the watts to a particular area, but you should be able to judicially combine the needs as well as the capacity. They should be, it's all are very, very intricate issues. The capacity that one can have in a particular system and also the demand that you can place on the system is something that one needs to assess properly. And people have not understood completely some of the systems. And what I want to say is that these are all the areas that are governing, the future. So one should look at, and all geotechnical engineers or the ground improvement engineers should look at devices. Say if somebody is going for piles as a source of energy, like as I said, thermal piles. Yeah, one need to understand instead of the use of stone columns to improve the bearing capacity is one thing, but use of a steel pile or some sort of thermal pile and then trying to recover heat or bring the heat to ground is something that's very innovative. So one needs to understand a lot of dynamics. So for example, people needs the knowledge of the thermal properties of the geomaterials, like hydraulic, the heat conductivity of the materials, then efficient characterization of the subsurface, the materials, the assessment of groundwater flow conditions, like water has a significant role in temperature reduction and increase and all that. And more than that, the ability to analyze the hydro, thermo, chemical and mechanical processes, like you have number of processes here. One is, the water related to and then thermal effects and also the chemical effects, the mechanical effects. They are all coupled in one sense that you try to recover heat from one source, but which is a function of the water as well as the temperature, and also there could be a chemist influence as well, and it is a mechanical process. Mechanics should be understood very well. Otherwise, the design of the heat recovery systems is quite complex. So, because you need to predict the both short term response as well as long term response. So, development of enhanced geothermal systems also requires advances in drilling technology. The conventional technologies are not as adequate. So, you may have to go for high temperature rock drilling for deep systems, controlled hydraulic fracturing in hot rock and analysis of induced seismicity. In fact, see, you need to do a hydraulic fracturing, breaking of the rocks in a controlled manner, and then you must see, the thing is the fact that the more you introduce a fracture leads to some sort of seismicity, like plate tectonics also should not be affected. Like we had the classical case of reservoir induced landslides, that should not be a case here. So one needs to understand that there should be a controlled way of doing this particular thing. So without advances in these areas, geothermal power production will be significantly limited. The knowledge that you have, maybe you may have a lot of ideas, but then if you do not understand exploit in a proper way, the problem is that it may lead to much more serious difficulties than what you initially thought of, and one should need a lot of careful analysis. So the other concept that I just mentioned was shallow geothermal heat pumps used in homes and commercial buildings utilize the thermal capacitance of the ground to transfer heat from the structure to the ground in the summer and from the ground to the structure in the winter. This is what people are trying to use in the case of what you call the in UK and other places. You try to have a thermal capacitance systems under the beneath the buildings, so that you have some sort of transfer mechanism. You try to store when it is available, and also when you need it, take from the stored energy. So this is a concept, and this needs a big change in our ground improvement knowledge and thinking, and even foundations, the way that we design and all that. So in most of the cases, the heat is transported via a fluid flowing through the long PVC pipes buried either in the horizontal or vertical loops. These systems have very high efficiencies, because as much as 85% of the total energy used may come from the ground. The thing is, some of the people have seen that, though, I mean, there are some calculations made on this, but one should, they say that there are highly energy efficient systems, and but the people have been using it. the geothermal heat pumps often require more than 100-meter deep boreholes or trenching 1 to 5 meters deep for single family home systems, or can incorporate the loops within the deep foundations for high-rise buildings and energy piles. So, the concept of these energy piles is what have been being followed in UK and other places. This was in fact I highlighted in one of the earlier lectures in the beginning, that when I discussed about the scope for ground improvement. So, you can see that it needs very deep boreholes, also trenching, in a deep level, which is not easy. Like if the cost of the boreholes, and it needs to understand that it's quite expensive as well. So, and then even having a loops within the deep foundations, particularly if you are trying to go for pile foundations, you need to have a system of piles, actually the energy piles. So, the use of the systems for residential heating, ventilation and air conditioning, like say for example, heat, vent and air conditioning systems is growing rapidly in Europe, as I just mentioned, and energy piles are becoming more common in commercial structures. In fact, people have to maintain an apartment, like you have an apartment, if the energy requirements are going to be too high, the problem is that it's not easy. So, the efficient design requires the thermal properties of the soil and any backfill material. The thing is that these systems need trenching and drilling and the use of the deep foundations. The efficient design requires the thermal properties of the soil and any backfill material used in boreholes. So, this is, say for example, as I just mentioned, the clays and sands and varieties of materials have varieties of one needs to understand the thermal response of these materials, and also the detailed information on the groundwater regime. The main difference in cost between a geothermal heat pump and the competing, as I said, heating, ventilating, air conditioning systems is the initial drilling or the trenching costs, plus thus the geotechnical can make the systems more competitive. Actually, the thing is, there are two issues here. The geothermal heat pump is one thing, GHP, and also the other one is also, like you need to understand these two systems very clearly, and and then geotechnical engineers have to understand a lot of mechanics here of the heat transfer in soils. So, energy piles have the additional constraint of being utilized for support. This is where the concept of geotechnical comes into picture, and the cyclic heating and cooling is something that affects the skin resistance of the piles, like as just mentioned. Steel pipes are being used, and definitely when you have cooling and heating of the piles, that will affect the skin resistance and may have some sort of settlements that are there because of this. And the long term efficiency of the GHP pipes or the systems including energy piles is significantly influenced by the balance between the cooling and heating loads. Like what is the cooling and heating loads? The thing is, as I said, the piles or the foundations that are now acting as energy recovery systems or energy storage systems are now subjected to cycles of cooling and heating. So we need to understand how is the efficiency of these materials, the cooling, and how is the heating influences the efficiency of the heat transfer is something that one. So, you need to understand the loads that one can expect, and also the ground temperatures, like how the ground temperatures also have a role in this. So, in addition to reducing the efficiency, sometimes what happens is that if the loads are not balanced, the ground temperatures gradually increase. Like what is required in this case is that, as I just mentioned, we need to understand the loads, like cooling and heating. What it means is that when as I said, in a particular winter and summer, in the case of winter, you need heat, so there is lot of load. but in the summer, you're trying to recover the that capacity. So you have to see the balance in such a way that they do not, your design of the system should not lead to inefficient design, and when the loads are not balanced, the ground temperatures gradually increase and decrease and dominates. In addition to reducing the efficiency of the pumping system, the temperature changes can extend beyond property lines. One should be careful about it. And see, particularly, the reason is that why I am mentioning is that people have been working on these lines, and of course, we in India at least are not aware of the impact that it has, and definitely use of this systems in highly congested areas like in Europe and all that, where the urban localities are more populated, they have a significant issues, because the ground temperature changes from one system to another thing could affect the neighboring systems and structures. Like, similar to you try to excavate a building here and then remove some soil, definitely it affects the stability of the next building. So in that sense, whatever changes you make here in the energy systems should not affect the next one, and this is very serious. So there are a lot of balancing that needs to be done, and research is required to develop inexpensive methods of evaluating the thermal properties of the ground. In fact, it's now we should say that we do not have very good methods of in situ methods. In fact, we should go for in situ methods of heat conductivity of the soil and all that, and also develop modeling tools and design methods for load balancing to prevent long temperature changes. It's like, you need to even use signal based signal processing techniques to see that if there is so much temperature raise, suddenly, there should be an automatic switch off and switch on systems like that, where your objective is essentially to get a balance. You can only take what you need. So that sort of balance should come, or store what you can store. And in excess of heat also leads to problems, and deficiency also leads to some problems. So these variations need to be catered for in the design of the heat recovery systems and the systems. So the other thing was that I just mentioned, the effects of thermal cycling is something that it needs to be understood, and all these things have to be examined in a careful manner. So uses of underground space for energy storage is something that people have understood very well in the recent times, and particularly in the area of rock mechanics and geological engineering, people have been doing a lot of work. Maybe in the broad spectrum of geotechnology it is not attempted, but at the same time, if you have a bigger picture, global picture, people are looking at geoengineering or ground engineering in a way that so that the energy can be stored. One important reason is that solar, tidal and wind energy are inherently intermittent, and they have a lot of fluctuations in the electricity production. So what people are trying to have is, they need to have a lot of energy storage systems in the ground to efficiently use the generated renewable power. So you have a lot of energy recovery systems, you need to really store them in a way that it can be done properly. So geomechanical systems such as pumped storage, hydroelectricity and compressed air offer the means of storing large amounts of out of peak energy to supply peak demand. What people have been trying to say is that you store the all the energy, or hydroelectricity is one way, like we always been doing it, and compressed air. In fact, you have to store this compressed air as a means of energy is something, compressed air has a lot of air pressure, the pressure energy. So that can be used as a storehouse, so that all the energy that you have can be stored to supply when there is a peak demand. Then there are people have been looking at salt caverns formed by solution mining, underground rock caverns created by excavating rock formations such as abandoned limestones or coal mines, and porous rock formations that can be used for compressed air storage. In fact, if there is an abandoned mine area and there is a storage area, you need to really properly redesign to see that it can work as a place for compressed air storage. Why not? It's a very complicated job, but you need to work towards that, and people particularly in France have been working on these things. So, the main geotechnical challenges in the development of compressed storage are there. For example, the response of the host rock to large amplitude cycles in pore fluid pressure, stiffness, strength and strains. Actually, what is happening, when you have compressed air has lot of pressure inside, and the in situ, if you store it in a particular material, it exerts lot of pressure on then. So, the stiffness, strength and strains that are induced because of the compressed air pressure needs to be understood in a proper manner. Then thermal fluctuations associated with gas compression and decompression, moisture changes and mineral solubility. I mean, even some of the rock materials, they are soluble. So, one need to understand, and the evolution, long term performance in the underground caverns are very, very important. One should understand that these are all very another issue that ground engineering or ground, though the title of the course is ground improvement, these are all, it's a ground engineering or what is called geoengineering. So, this is some example of how the response time for different energy storage is there. Say for example, energy kilowatt hours and the response time, and you can see the power and then the energy, and batteries have very quick response systems because the batteries, their response time is faster. Then you also have fuel cells, they are somewhat here, and pumped hydro storage is somewhere here, and compressed air energy storage is here. What I meant was that they may have low response time. So, definitely this is some sort of understanding, actually similar to stand up time in soils, like sands have less stand up time and clays have a more stand up time when you do an excavation. So, these are all some sort of work people have done to understand what is going to happen when you are trying to, how is the response time. So, this is also so for example, this is also quite important in the case of different energy systems. Other important point that I would like to see is that people have been looking at radioactive solid waste, and you need to contain that in a proper way, and nuclear power generation embodies very low CO2s. The advantage of the nuclear radioactive waste is that it has low carbon emissions are there, and the use of the nuclear reactors will demand the development of long term radioactive waste repositories. People have been working on this, and people, though the nuclear energy is thought of as a serious alternative, there is a setback in because of the incidents of the earthquake and tsunami in Japan, but I think still people are trying to pursue that, and it's more of engineering, and it's a very critical engineering, and definitely geotechnical has a big role to play in trying to address the issues of nuclear energy at all stages. Say for example, mining of the radioactive waste, how do you handle that? Foundations of nuclear power plants, static and dynamic design, heat absorption for new generation materials, spent fuel pools, how do you handle the spent fuel, and geophysical monitoring and leak detection, bioremediation, waste repositories. There are many issues that you have, and a series of natural and engineered barriers to contain waste that will be carefully prepared, packaged and placed in excavated tunnels is something that people have been looking at, but then the stability of the engineered barriers is needs to be assessed through number of experimental studies and detailed studies and simulations. This is actually people in Baba Atomic Energy, Atomic Center and Department of Atomic Energy, they handle this, and of course the role of geoengineering or ground improvement or geotechnical engineering is quite significant in all these issues. And potential geological formations include salt, hard rock or clay to minimize the amount of radioactive waste that may eventually be transported away from a repository and reach the human environment. So, many of these environments need to see properly, and as I just mentioned, significant reduction in carbon emissions could be realized by implementing carbon capture and storage methods, and so that the objective is that that there is a carbon emissions, try to capture it, okay, so that it does not really heat the atmosphere. There is another way of people are working on that. And development of efficient carbon capture technologies to remove CO2 from plumes emitted from coal burning plants and kilns used in Portland cement production is something that people have been looking at it. Robust technology is available to inject CO2 into the ground. However, significant geotechnical uncertainties remain related to geological storage, including identification, characterization of suitable formations, continuity and long-term stability of the sealing layers, long-term performance and grouts and well plugs. There are so many issues that people have been trying to do. So, for example, capturing of the carbon, you can see from a particular plant, it can, how do you do that? This is all one schematic way. This is another schematic way of trying to capture the carbon at various levels, and this is what we call carbon capturing geological sequestration. So, people need to understand the energy options in a different way, and also see that there is some integrated reviews of various ways of reducing the carbon emissions, and also carbon sequestration, nuclear generation and renewable sources such as. So, you should have an integrated view of the carbon emissions as well as the leak. It is a serious issue. One should understand them in a proper way. Otherwise, if you don't have, this is a saying that if you don't know what right hand is doing, what left hand is doing, right hand doesn't know. So, that should not really happen in the case of energy. And people have been looking at sustainable use of geomaterials, like again the use of waste. I think solid waste. So, there have been people have been doing that. Maybe this I will address that in another lecture, where the sustainable waste generation requires that the rate of waste generation does not exceed our ability to either reuse or dispose of it, like particularly in, say for example, the case of landfills or the hazardous waste materials. So, you need to even contain the waste, reuse the waste in a proper way, that the waste is used properly. So, that way the geotechnical plays a big role in the efficient use of natural resources, recycling, more comprehensive use of the virgin materials and energy efficiency. It reduces the volume of waste, engineered waste reuse in long term performance, developing engineered waste containment systems, which is very, very important. And there are a lot of challenges, and definitely in the climate, to prevent the effect of the climate change, the geotechnical is quite helpful. The effects on geosystems is quite helpful, and this is a serious issue. And sustainable design against multiple hazards is something that also is a serious issue, because like when you do something else happens, like you try to do hydraulic fracturing, it should not lead to earthquakes. This is something that one should understand. So, sustainable design is something against that's what I meant by multiple hazards. So, for example, dynamic salt structure interaction effects for wind turbine foundations, and they may be subjected to earthquake loading and dynamic cycle loading from superstructure. So, some of these issues need to be addressed in a simple way, and enhanced use of ground space is another important issue. And so proper geotechnical engineering, life cycle cost analysis, underground utilization, innovations should be there, side innovations should be there. There should also be self-adaptive tools, excavated materials and good support systems. And you also have whatever is considered standard may not be applicable here. So, you need to have innovative ways of doing things. One should look at many innovative methods of geotechnical issues in energy geotechnology. And say for example, crumpled processes, shear fractures, and most problems in sustainable geotechnical engineering are something very complex. One should see that there are also biological phenomena, and also spatial variability of many of the geological properties and geotechnical properties, very, very significant, and one should understand that they have a lot of things that one can do that. So, what I would like to say is that geotechnical engineering has a significant role in controlling this, and I must say that the people have to significantly use in the geotechnical curriculum, and have a look at it. These are some references. Thank you.